So hello everyone. We are back here with topic number 2 for part 3, where we're gonna actually cover the design of rectangular beams and one-way slabs. As you recall from the previous two recording, we focused on analyzing the cross section to get the nominal flexure strength and also identify the phi value so we can get the phi mn, which is the ultimate strength of the cross section. And we also focused on the rectangular section only up to this recording. So before we dive deep to this part of the recording, uh, let's recap what we did before. So very much every time we ask you to calculate phi mn for a cross section, which is the ultimate strength of a cross section, we always provide you with everything. So we provide you with the width p. We also give you the structural depth d, which is the distance from compression fibers to the centroid of the reinforcement. And we also give you the area of reinforcement as or number of reinforcement and the size of the reinforcement. And we also provide you with the F prime C and F yield of the reinforcing steel. However, when you do design, most likely you will not be able to identify the area of steel needed for your cross section, and also sometimes you will not be able to first guess the values for the width of the cross section for the rectangular section and also the structure depth. So the first few slides here, we trying to give you some guidance from ACI how to calculate the overall depth, not the structure depth, of any rectangular or one-way slabs. So here, the H value, which is the overall depth, can be defined as starting point here from table 731-1 for one-way slabs. So very much if you have a slab where this slab is actually supported over beams, but it is simply supported, you will take the span of the slab L and divide it by 20, and this will be your minimum overall depth of the slab H. If the slab actually is continuous from one side, you will actually need to take the span. This is from one side. Let's make it continuous from one side. So this slab is continuous from one side because in this side there is nothing, and this slab is also continuous from one side. There's nothing. So you can take the span and divide by 24. Make sure that you take the larger span of the two because you have to have uniform slab. If actually you have a slab, which is this case, continuous from both sides, this continuous from both sides will have, let's say, this is the first span, and this is the second span, and this is the third span. So this slab is continuous from both sides. And this part of the slab is continuous from one side and similarly from one side. So to focus on this one, you'll take the span of this slab, the second one, and you divide by 28, or the span of the outer ones, first one and third one, divided that by 24. If you have cantilever slab, which is a slab that extends from one side as a cantilever, you take the span divided by L. There is a note here that this table was developed for reinforcement uh, of grade 60 or a field of 60,000 psi, and in order to account for any other types of steels, if you have a field is more than 60,000 psi, you have to apply this equation, which is zero point 0.4 plus a field divided by 100,000. Similarly, this is, as we discussed up to now, is for one-way slabs. For beams, rectangular beams, we have similar table. Now table will be 9.3.1-1 with minimum depth of non-pre-stressed beams. Similarly, if it's simply supported beam, you take the span, but now you divide it by 16 instead of 20. One end continuous, you will take a span divided by 18.5. And if it's continuous from both sides, it's a span divided by 21. And if it's cantilever part of the beam, it will be L divided by 8. Similarly, we have the same factor to adjust if you are using any other steel more than 60,000 psi. So now this slide provides you with the initial guess of the overall depth of the cross section each. Also, we now learned how to get a guidance on the total depth of a rectangular section each. This slide is showing for you the bar size. So you have bar size from 3 up to 18, and this column gives you the nominal area, and this column provides you with the nominal, the second column is providing you nominal diameter, and third column is providing you with nominal area. So for example, if you have to use one of those bar sizes, let's say number 8, size number 8, you will directly get the area AS for this bar. And if you're using 3 of them, you have to multiply this number by 3. Uh, Oftentimes, if you use number 9, the area is 1, so it's going to be equal to the number of rebar. So make sure that depends on what area you are using. Don't forget to calculate to get the nominal area from this table. It's just very easy way to calculate it based on ACI. As we mentioned a couple of slides ago, that we were able to get the overall depth H. However, one will focus on one important distance, which is the structure depth D, which is the distance from the extreme fiber in compression to the centroid of the rebar. So in order to do so, if you actually draw this in very detailed manner to scale, you will see that in any cross section you have number of bars, whatever bar size is. You have to get what's so-called concrete cover here, which is the distance from the extreme tension fiber of concrete to the first steel that you will face, which is in this case will be the stirrups. And we will learn a lot about stirrups in topic number 4, shear, but stirrups rule are to resist shear, so it's mainly shear reinforcement, and also to position the top rebar here, as you can see. So in order to develop the cage, you need always at minimum 2 bars at the top side, so you can hang the stirrups. Some rules for the stirrups here: if you are using longitudinal reinforcement of size number 10 or smaller, you have to use at least bar number 3 for the stirrups, which with the area with a diameter of 3/8. This is the stirrup. The stirrups oftentimes is a straight bar that we actually bend in this shape to shape a stirrup. if you're actually using bar size of 11 or more, you cannot use number 3, you have to use number 4. And in order to get to the what's so called, we call this concrete cover, and this is what we need to know, which is the distance from the centroid of the rebar to the edge of the concrete. This is called structural cover. It's called a structure cover here. So the structure cover is actually is concrete cover plus the diameter of the stirrup plus half the diameter of the rebar in this case. So let's say in this case we have 1.5 concrete cover, and let's assume this is bar number 10. So in bar number 10 you use 3/8 of an inch, and this will be the diameter of this bar. So you're gonna use 3/8 plus 3/8. This gets you from the extreme fibering tension to the top level of the stirrups. And now you are using bar number 10. Bar number 10 nominal diameter is 10/8, but you need to the centroid of it, so you have to multiply times 5, and this will get you the cover or structure cover, which you need to deduct from H to get your D value. So someone will ask how we define the concrete cover, because we know how to get the size of the stirrups. We know maybe we start guessing the rebar size we need to use. And however, how to get the cover of the concrete? If you consult ACI table 20.5.1.3-1, this table provides you with minimum concrete cover for different cases of concrete. So if you have concrete cast against permanent contact with ground, so ground means that you may be exposed to water, the stirrups, sorry, the concrete cover has to be at least 3 inches. If you are exposed to weather or in contact with ground, in this case you are 2. If you're number 6 through number 18, or 1.5, and all other cases when you are not exposed to the ground. Oftentimes we will provide you in the exam or homework or quizzes with this number, or even a structure cut. Also, as you remember from topic number 1, we covered pretty much the minimum aggregate size. But however, here what we need to do is ACI actually decide the minimum clearance between the rebar here. So here, if you say like you use tree number 10, you need to check this minimum distance. This minimum distance has to be at least the bar diameter, or 1 inch, or 4/3 of the aggregate size you are using. So let's go through an example here, very detailed example. Design a rectangular beam of 22 feet long simple span to carry a dead load of 1, not including the weight of the beam, and live load of 2 kip per foot. So the dead load is 1 kip foot. We are not including the beam load in this 1 kip foot, so I have to calculate it. Live load is 2 kip foot per foot. Concrete is F prime C was 4,000 psi, and steel grade of 60 mean that it's a field of 60,000 psi. So if it's simply supported beam, you have to be a minimum depth of L divided by 20. So in this case, I actually used L divided by 10. So H is 0.1 times the span. This actually gives you 2.2 feet, which is approximately 27 inches. You start with the cover of 2.5, you get D of 24.5. If there is no assumption, 2.5 or 3 is a good assumption for cover to convert from H to structure depth D. Always I prefer to use B as equal H by divided by 2, that give you 14 inches. Now we can calculate the weight of the beam as we learned from the topic number 1. It's a cross-section area in inches square divided by 144 to convert it to feet square. So 27 by 14 divided by 144 and times 150, which is pound per cubic feet unit weight of concrete. This gives you 3,394 pound per foot, or 0.39, sorry, 3, get it again, 0.394 kip foot if you calculate kip per foot. So this is part of the dead load. If you add it to 1, this is a total dead load, and you also have 2, which is a live load. Remember the load combination for ACI, 1.2 for dead load and 1.6 for live load. So you multiply 1.2 times 1.394 plus 1.6 times 2, it give you 4.873 kb per foot. It's simply supported beam with uniform load, so the moment is always W square over 8. So it's going to be 4.873 times 22 squared divided by 8. It gives you 294.8 kb foot. To go to do the design, actually, to do the design, we know always we compare phi man to has to be more or equal m ultimate from loads, which we just calculated. So if you assume that you can get mn, if assuming phi is 0.9, which is most likely you have to be, mn will be has to be more than or equal m ultimate divided by phi. M ultimate we just calculated as 294.8 from the loads, we divided by 0.9. So our m nominal has to be more than 327.6 kb foot. You know always T is AS divided by F yield, assuming steel is yielded, because this is the main assumption. Even we have to make the steel yielding over 0.005 strains. Concrete is compression is 0.85 F prime C AB, correct? You know C equal T, and M nominal moment is equal C or T multiplied by arm. So this is C value, we're going to use it, and arm is D minus A over 2. You have the value Mn here. You can multiply times 12 to convert it to inches, keep inches, by 100 to make it pound inches. In this equation, you can see A is unknown, but B you just calculate as 14. D you can just calculate at 4.5. F prime C given as 4,000 psi, so you put 0.85 times F prime C 4,000 psi times B times A times 24.5 minus A over 2. You solve this equation here, 0.5 A square minus 24.5 A plus 82.588 equals 0. It gives you A value as 3.64 inches. Now you can calculate the value C, because now you got A value, and from C equal T, the C part of the equation is 0.85 times 400 times A here, which is 3.64 times 14, and equal AS is unknown because you don't know AS yet, times 60,000 psi of yielding of steel. If you solve this equation, AS would be 2.89 inch square. We can use here 3 number 9, because number 9 area is 1 inch square, times 3 give you 3 inches square, which is more than AS. Now we can start the process from here. Is exactly similar to topic 1-1 and 2-1 and 2-2, where we get the nominal flexure strength. So A is AS a field divided by 0.85 F prime C B. You got 3 inches inch square for AS. If you 60,000 psi divided by 0.5 divided by 400 divided by 14. 400 is for F prime C. 14 is a width B. This gives you 3 as 3 A as 3.78 inches. You can actually calculate C here by dividing A by beta 1. In this case, F prime C is 4,000 psi, so beta 1 is 0.85, as you know, so C is 4.47. You can get epsilon T, strain enforcement, as D minus C divided by C times 0.03. This gives you strain of 0.0134, which is way more than 0.05. Phi in this case is 0.9, and you calculate Mn as A as a field times D minus A over 2. AS is 3 inch square, a field is 60,000 psi, D is 24.5, A is just calculated at 3.78 divided by 2. This gives you moment of 339.1. If you multiply this number by 0.9, which is the phi value, you get 305.2, which is more than M ultimate from loads, which is 294.8, which just calculated from previous slide. Thank you all for tuning in. In order to finalize topic number 2, we have one more recording to cover both design of T sections and also design of doubly reinforced sections. Thank you.